Bismillah Rahman Rahim. Um, this is going to be the first lecture on graph theory. So, you are already familiar with the concept of graphs in the previous semesters in discrete mathematics and data structures. You have already done what is the graph. So, let's start with the definition of a graph. So, what is a graph? So graph is basically a set of vertices and edges. Now, mm, so many problems like uh, there are lots of application of the graph theory in which graph works as a backbone of that application, just like internet, just like network protocols, just like path planning, and many more. So today basically we will start our lecture. I will not go in depth in detail of what is the graph and how we come across with the graph. So because you are well familiar with that one. So we will start with the different kind of graphs. So there are graphs with respect to cycles. So we can say that the graph can be cyclic or the graph can be acyclic, and graph can be with respect to connections. So we can say that the graph can be connected as well as unconnected. Graph can be directed with respect to direction. So the graph can be directed as well as undirected. So undirected means both directions. Then graph can be with respect to weights. So graph can be weighted as well as graph can be unweighted. So let's start with the uh, directed graphs. Okay. So the directed graph is a graph which is which in which every edge is having a direction. So vertices are in the graph. Vertices are denoted by the circle and the edges are denoted by the arrows. So let's say we have a graph like this one, a short one. So vertex is being every edge is having a direction. So let's say this is vertex A, vertex B, and vertex C. So from A to you can move from A to B, and you can move from B to C, and you can move from C to A, but you cannot move from A to C or the other way. So this is a directed graph. And in undirected graph, there would be both direction, but the arrow is not defined. So direction is bidirectional. So there is no sign of arrow on this line. So it means you can move from A to B and also B to from B to A. And in this way, if this is C, then you can move from B to C and then C to B also. In the same way, if you talk about the connected graph is a graph in which every vertex is connected with the edge. So there is no edge or there is no vertex on which you cannot reach from any other vertex. But in unconnected graphs, the graph is disconnected or in the multiple components. So like this one, so this part is independent of this part, so that if you start from here you cannot reach on these vertices. So this is unconnected graph. The next we come to the cyclic graph versus the acyclic graphs. Cyclic graphs are the graph in which there is at least one cycle in the graph. If there is a once at least one cycle in the graph, then this graph would be called is a cyclic graph. So for example, so this is a cycle. Actually, the let's start from A, we move to B on the arrows, B to C and C to A. So if you are reaching again to the vertex that was already traversed, so it means there is a cycle. So if a graph is having a cycle, then the graph would be called cyclic. And if there is no cycle in the graph, then the graph would be called acyclic, just like this one. So 8 we can move from A to B, B to C, but we cannot move from C to A. So this graph is acyclic. Um, the last parameter that we were discussing is the weights. On the basis of weights, the graph can be weighted or the graph can be unweighted. If the cost of every edge is defined, so then it would be a weighted graph. So in this scenario, so every edge must have some cost. And in unweighted graph, so the cost of every edge is considered the same, or we can call them one, so but it is not defined in the figures. So whenever we draw our graph, a random graph, so it always carried at least one of the four parameters of we discussed previously. So just like this one, so we will call it, this is a directed weighted acyclic connected graph. In the same way, if we draw some other graph, so it can be, so let's say it's not having the arrow, it's a straight line. So it is A, B and C. So we can call it undirected unweighted connected cyclic graph. Now, so first we discuss from where these graphs come. Let's say we have different cities: Lahore, Multan, Gujranwala, Islamabad, Faisalabad, and their distances are 170 kilometers, 120 kilometers, 300 kilometers from Lahore to Multan. Gujranwala is 160 kilometers. If you travel on the uh, GT road, so this is the GT road, and if you travel from Lahore to Islamabad on motorway, then it is 380 kilometers. So, and we need to find best path from Lahore to Islamabad. So this is our problem. So you can be related with the shortest path problem. When we come across a real life problem, so what we do is, so we have a real life problem and we convert it into graph theoretic problem. So and then we convert our real life problem into a theoretical problem. For example, I just converted this real life scenario into a graph where every city is converted into a vertex and the road link between the two cities is converted into the edges. So this is how we convert our real life problems into a graph theoretic problem. And from there we find solution, that is actually the algorithm, and then we apply their solution to the real life problem again, and how this real life problem is now solved. Now let's discuss the implementation and the representation of graph in computer, because this is just that we have already discussed are the just are the mental pictures of the graph. So we have to discuss and understand how we can store our graph into a. Basically, there are two implementation or representation of a graph in computer. One is called adjacency matrix representation, and the other one is adjacency list. So the question is, which one is the better one? So it depends upon the algorithm, and the combination makes algorithm works the best. Sometimes adjacency matrix works better than adjacency list, and some other time adjacency list works better than the adjacency matrix. So now it depends on the scenario and the algorithm. So how these things are being executed. In adjacency matrix representation, if there are four vertices, just like in this graph there are four vertices, so we need a matrix or two-dimensional array of 4 by 4. And then how we store this one? So every edge is stored in this one. So just like this edge is a to moving from a to b, so this is the cell for this edge, so we will store its weight, that is 3. Okay, so there is no edge from a to a, so that is 0. From a to c there is an edge having cost 2, and then there is no edge that is moving from a to d, so that is again absent. So and the other one is b. From b to a there is no edge. From b to b there is no edge. From b to c there is an edge having cost 5. From b to d there is an edge having cost 4. And the same way coming to the c, there is no edge from c to a, so that is 0. C to b there is no edge. C to c there is no edge, and c to d is cost is -3. And from d there is no edge moving to any other vertex. So this is how it is done. So if this graph were uh, unweighted, so we would be storing 1 in place of these costs, because there would not be if it were unweighted, so there would be no cost represented on these edges. And if it graph were of undirected, so it means you will be marking a to b and b to a with the same cost. So just remember these things. In adjacency list representation, uh, if we take the same graph, so we need an array of size 4. So there are 4 vertices, so we need a array of linked lists. So this is an array of linked list. So this is index 0, 1, 2 and 3. And now, so this is for let's say a, b, c and d. So in this list all the adjacents, or we can call them all the neighbors, are recorded. Just like there are two neighbors of a, that is a, b and c, so we will store b here and c here as a chain, and the chain closes here. And b, so there are two vertices, that is c and d, that are the neighbors of b, so we store here, so d and c, so these are the two neighbors of b, so that is the adjacents. C, so there is only one neighbor of c here, you can see it here, so there is only one neighbor of c, that is d. Okay, and here we can see that d is having no neighbor, so no adjacent, so that means it is having no list. So this is how adjacency list and adjacency matrix are used to represent a graph. The next question that comes to the mind is, if this is graph is just like this is a graph, so if this is a mental picture, then and we can store it in a matrix or in the adjacency list, so how a user can input a graph. So there are, you may have a different method for yourself, but what comes to my mind right now is you just get the number of vertices. There are, user will give you 5 or 10 or whatever, so you can use that number in a loop. I was discussing how the graph inputs are can be taken from the user. So just get the number of vertices and then repeatedly get the neighbors. Let's say in a loop you pick a vertex, let's say one vertex 1, and then get all the neighbors of vertex 1 from the user and store them accordingly in the matrix or the linked list, and repeat that one for all the vertices. So this is how you can get the end user input from of graph from user. We always devise new data structures to improve the data storage as well as the search operations. So just like any other data structure, we need to search graph also. So there are two algorithms that are called breadth first search, that covers breadth first and then it goes into the depth. The second one is depth first search, that covers depth and then it covers the breadth. In both cases, the both algorithms cover all the vertices, but both have their own advantages and disadvantages. So let's start with the algorithm breadth first search. So let's have this graph, and if you open your Coleman's book, you can see the algorithm. So I will request you guys to open that algorithm first, and then we will execute this whole algorithm. So three arrays are being used in this algorithm, that is distance, color and parent. We will do on the as figuratively as well as in the changes in the data structure. You can see in the algorithm that from the line 1 to line 4, that is the initialization of this data structure. So there are basically 8 vertices: A, B, C, D, E, F, G and H. So the distance of every vertex is marked as infinity, and then the color of every vertex is marked as white. So I use W as a white. So there are the changes in this color from white to gray and then gray to black, and then then every parent is marked as nil. So afterwards we will be storing the parent of that vertex in this place. So the same, I just mark the distance of every vertex, that is infinity, here at this point. After the general initialization, there is a another initialization, that is of source starting point. So let's consider A as our source vertex. So the color of, and this one is marked as gray. Color is marked as gray, and then its distance is marked as 0. So its distance is marked as 0, and its parent is marked as nil. And then so empty queue is created, and the source, our source is inserted in it, that is A. And then from the line number 10 our main algorithm starts, and it says the while q is not equal to null, you just dq u is equal to you dq. So dq you will get a from here, and then you will check all its neighbors, and there is a loop on the line number 12. There is a loop for each v belongs to g dot adjacent of u, so there is a loop for all the adjacents of a. So we will store all adjacents one by one in v, and then we will continue the process for each v. For each v, for there are basically two adjacents b and e, so we can pick any one. So let's call it b. Okay, now we have to check whether the color of b is white. So the color of b is white. If it is white, then we have to do four things. Remember, we have to do four things. The three is the updation of these three arrays, and one is we have to place back into this vertex into q. Now, so if this one is this is the scenario, so we mark it. So this was gray, so we'll mark it as gray. Okay, so the color of b is now gray. Its parent is marked as a, b's parent is marked as a is the parent of b, and the distance is the distance of its parents plus 1, so that is 0 plus 1 is 1, so the distance is now 1, and then we place this b into this q. So this a is not there, so it's gone. Now we go for the next neighbor. Now that's the next neighbor is e, so we pick e here. Then we do the same things. We mark the parent, we mark change its color, and we change the distance, that is 0 plus 1 is 1. So its distance is 1, its color is now gray, and its parent is a. So now we can see that there is no other neighbor of this one. So this is the loop of adjacents will terminate, and now it will change the color of a from gray to black. So the color of a is changed from gray to black. So that means it has played all its role in the execution of this algorithm. So now we forgot to place it into e. Again come to the line number 10, and then we dequeue an element, line number 10, and dequeue an element and place it in u. So both have 1, so that is b will be here. Now we have to find all the neighbors of b. So there is a neighbor of b that is a, but it is not 5, so we'll skip it. There is another neighbor that is e, so again it is not white, so we'll skip it. And then we'll find another neighbor that is f. Now it is white, so we will perform 4 steps on this one that we performed on b and e. So now what will happen, so we change it, we mark b as a parent of f, we change the color of f to gray, and we mark the distance, that is 1 plus 1 is 2. So the distance of f is 2, the color is gray, and the parent is marked as, what is the parent, that is b. And then we've placed this f into q, insert this one in q. So this is all done with. Now there is no other neighbor of b, so the loop will terminate and it will change the color of b to black. So changing the color of B to black, and then we will extract another dequeue another element from the queue, that is B. So B is already done, so now we will get E. Coming to E, so its neighbor is A, but its color is not white. Another neighbor is B, but it is not white, so there is no other neighbor, so we will just change its color and move back. So the color of E is now black, so that means it has completed its role in this algorithm, in the execution of this algorithm. Coming forward, so next element that we will extract from the queue would be F. So it is F, so we are here now. So in this way we will continue this algorithm, placing the elements into queues. And so in this way we can continue our task. So F is having only one neighbor, that is C, so its color is its distance is marked 3, its color is marked gray, and its parent is marked as F, and then we placed this C into the queue. We mark the color of F black because there is no more neighbors other than the C, so we mark the color of F is black. And then next we extracted G from the C from the queue, and then we mark this parent. The distance will be 4, that is 3 plus 1 4, and its color will be gray, and then it will be placed in Q, that is G. The next we extracted G from the Q, and now we will see all the neighbors of G and we'll explore them. Now we have explored D and H one by one. So the color of D is changed to gray. Its parent marked as G is marked as a parent of D, and its distance is marked as 5. And the same is with H. And we have now placed both in Q, that is D and H. Now we will extract another element from the Q, that is D. So D has neighbor G, but it is it was marked as black in the previous iteration, but it is now exploding from D. So its G is a neighbor, but it is not white, so we'll skip it. And then there is another neighbor of D, that is H, so it is also not white, so we will skip it. And then we will mark D as a black, and we mark D as black, and we'll continue with the new vertex, that is H, extracted from the Q. So there are two neighbors of H, that is D, but D is not white, so we'll skip it. And then there is another neighbor, that is G. G is also not white, so we will skip it. So at the end we will mark its color to black. So the color of H is now black. So here our algorithm terminates. So you can see, so the algorithm, so every color is now black. So this is the tree that we have, that is called the BFS tree, that is stored in this array parent. And then these are the distances. If we can use in any application, we can use them. We can generate a BFS tree from this algorithm, that is the output of this algorithm. So all these parents that are marked above are just mentioned here in this tree. So A to E, they are A to B, and from B to move to F. from F2 we move to C. So C2 we move to G. I have a bad example here, so I have to move it here, G, and from G there are two vertices, that is D and H. So this is a BFS tree. The main purpose of this tree is the search one, but the side advantage is gives the shortest path. It is also the shortest path tree from source to every other vertex for unweighted graph. Okay, the time complexity of this algorithm is big of v plus e, that we will discuss in length in our next lecture. So I hope you will be able to understand this one. So if you have any problem, please don't hesitate to discuss in the comments or in the group. So thank you very much, guys. Thank you. Allah Hafiz.